Okay, hello everyone. You can hear me well? Few yes or no would be appreciated. Can people hear me? Okay, thank you. Good morning for some of you, good afternoon for some of the rest of you, I guess. Okay, so thanks for continuing on this class. So as promised yesterday, I told you that today we are going to be talking about positroids. So today's topic. And so I'll give you some definitions regarding this and the combinatorics behind it and how this is related to what we did yesterday and what we are trying to accomplish by Thursday. But maybe since we are talking about matroids and everything, so probably you guys already know that this morning the Fields medals were awarded, and so one of them is given to Junho, and Junho has solved some of the long-standing conjectures in combinatorics regarding matroids. So it's not the kind of things that we're going to present here. It's not related to what he has done in his work. But anyway, matroids are very appealing for many reasons, so that's very nice. And also as a woman in mathematics, I'm very happy that Marina Wiasowska also is one of the awardees, and I hope that women's work in mathematics keeps being recognized. And okay, so without further ado, so let's start with recapping a little bit a couple of the things we did yesterday. So we had that, so we know the following. If we take a point in the Grassmannian Kn, so again a k-dimensional vector space inside Rn, then this point we can represent it by a full rank k by n matrix. The choice is not unique, it depends of what bases do a pick for V, and I have infinitely many choices for it, but any such matrix does the job of representing V, and they are all related by row operations. And so this matrix here has n columns, and also we know that these columns, along with the linear independence relations among them, give rise to a matroid. And so this defines a matroid that we can denote either M sub A or M sub V. And this is a matroid on the ground set N, given by the set of columns and the collection of bases, where we know that someone here, some K subset is an element here, if that K subset is a basis for the column space. And another way of saying that is that if I happen to have a collection of K vectors from my column space that are a basis, it means that the determinant of the submatrix that they form is non-zero. So, in other words, an element here is characterized by the condition that the determinant of the submatrix that I take from A by just picking the columns indexed by V is different from 0. I'm going to denote that by delta V. And so this delta V just denotes the determinant of the K by K submatrix of A, indexed by columns I1 up to IK, where precisely those are the elements of V, of capital B, I mean. So it is the condition that characterizes the basis when I have a linear or representable matrix. Okay, so this is recap from yesterday. And any representable matrix arises this way, namely any representable matrix can be obtained. Any representable matrix on ground set N of rank K can be obtained or can be thought of as a point in the Grassmannian Kn. Okay, so anyway, this notation is new, and if it's not clear, please let me know. But basically, this just means you're taking a K by K determinant formed by the submatrix whose columns are indexed by the elements in B. Okay. Okay, so I'm gonna define what we will call the totally non-negative Grassmannian. If I were to write here in the middle, it can be okay. So then I'll stick to this side. So the totally non-negative Grassmannian so the totally non-negative Grassmannian, which we are going to denote GRKN and with a bigger than or equal to 0 on top, is this subset is the subset of the Grassmannian. So is the subset of k-dimensional vector spaces for which there exists a matrix that represents it in such a way that that matrix, when we check this condition, any k by k subdeterminant of that matrix is either 0 or strictly bigger than 0. So basically, any maximal minor of my matrix is bigger than or equal to 0. So this consists of such vector spaces. So vector spaces for which there exists k by n matrix with the property that delta B is bigger than or equal to 0 for all B subset of size k of my column set. Oh, I should say such that there exists a matrix A representing it for which this condition is satisfied. Okay, so let's do an example. So basically here I'm just saying, in this definition, I'm just saying that whenever I have a vector space and I'm lucky enough to find a matrix or a basis that represents it, and if I were to compute all the maximal minors of that matrix and all the maximal minors are bigger than or equal to 0, I can conclude that my point, that point in the Grassmannian actually belongs to the totally non-negative Grassmannian. Okay, but of course it is tricky already to determine among all the infinitely many representations that a point in the Grassmannian has, is it the case that I'm able to come up with such a representation with this non-negative condition? And that's precisely what brings us to the definition, one way of defining what a positroid is. So I'm going to do a few examples, but before that, so let me give that definition, and then we will define them. So a positroid. So a positroid is a matrix, it's a representable matrix. So is a matrix, is a representable matrix or linear So as a matrix, we know it's defined by a pair given by a ground set and a collection of bases. It's a representable matrix for which there is a matrix in the totally non-negative Grassmannian that gives rise to it. So I'm just going to say for which there is a matrix in the totally non-negative Grassmannian, such that when I look at what matrix does it bring me to, so whose underlying matrix is precisely P. Okay, so I'm just saying positroids are the linear matrix coming from the totally non-negative part of the Grassmannian. That's what I'm saying here. So let's start with some examples. So, okay, so let's take this one. So I'm going to take this pair. So my ground set here is going to be 5. And this is going to be something of rank 2, where here my collection B consists of the subsets of size 2 given by 1, 3, 1, 4, 1, 5, 3, 4, 3, 5, 4, 5. So I claim that this is a positroid. So if I say this, if I'm claiming this, so I'm saying already too many things. First of all, I'm saying this pair is a matrix. So this collection of bases satisfies the exchange axiom. And moreover, not only is a matrix, but it's a representable matrix. And is a matrix that I can represent via a point in the totally non-negative Grassmannian. So there are lots of things going on behind this. And if I were just to appeal to the definition of what a positroid is, then I would need to be able to come up with a matrix that gives rise to this P as its underlying matrix. So if I were to do that, what should be the size of the matrix I need to construct? What do you guys say? Can you tell me what should be the matrix that, or what should be the size of the matrix that we should be looking to? 2 by 5, exactly, yeah, because this has rank 2 and my ground set is 5, so we have 2 rows and 5 columns. And so if I were to take the matrix, I'll take this one here, and if I did my computations correct, then my claim holds. So if we were to label the columns of this matrix, so it should be the case that each one of these 2 subsets, each one of the, here I'm missing something, here is a 4, 5. Each one of these subsets of size 2 should be such that when I compute the determinant, the maximal minor index by them, it should be strictly bigger than 0. The rest of the minors should be equal to 0. So for instance, if we were to take 1, 5, then I look at columns 1 and 5. 1 and 5 form the matrix given by these 2 guys, and that has determinant 2. And the same should happen with the others. I'm not going to check it right now, but maybe you guys can check that I did it correctly. If not, please let me know. And for instance, what is a subset of size 2 that is not a basis out of this example? That's a question for you. You all in the audience, I mean. So can you give me an example of a subset of size 2 that is not part of my basis set? So Wendy says, so columns 1 and 2, exactly. So columns 1 and 2, so the set 1, 2 is not part of my basis set because its determinant is 0, and we see also that it's not part of this collection here. And it should be the case that if we were to check all the subsets of size 2 out of my set of size 5, only these ones give me determinants bigger than 0, the rest are going to give me 0. Okay? And also Wendy, hola Wendy, as Wendy points out, so certainly this subset of size 2 containing columns 1 and 2 gives us 0, And also you can see that any subset that contains column 2 is going to give you 0. Okay? So column 2 is one, or element 2 is an element that is not going to belong to any basis. Okay? Okay, cool. So questions? Okay. So do you see something strange about this definition or something that makes you uncomfortable? I do, even though I have worked with these things for a while already. But if you are given this definition of what a positroid is, what would be your thoughts about it? If you were to check, if you would like to check that something is or is not a positroid, how do you come up with a matrix like this if it's not by trial and error? That's already a definition that is tricky to work with, because you certainly are not going to check, you are not capable of check the infinitely many options of all the matrices that potentially represent a given linear matrix. So you need to come up with a better strategy to check whether or not something is a positroid. And that's part of the tools that I want to provide you with today. Okay. So far, I have just given this definition of the positroids are coming from points totally non-negative Grassmannian. Certainly the totally non-negative Grassmannian is a subset of the Grassmannian, but so far we are not convinced that it's a proper subset. If it were not, this definition wouldn't make any sense. So now I want to give you a non-example. Yes, I want to give you a non-example. So let's take, yes, you can see there. So I'm going to take a matrix on ground set 4 with basis set given by, so I'll take these guys. I'll take 1, 2, 1, 4, 2, 3, 2, 4. Okay? So I claim that this is not a positroid, although it's linear. So even though this is a matrix that comes from a point in the Grassmannian, it's not a matrix that can be realized in the totally non-negative Grassmannian. So let's see why that's the case. So this is a smaller example, so we can certainly manage it. So already we see who should the basis be, and already we see who the ground set is. So we can argue just by trying and see that no matter how hard we try, we are not able to provide a matrix that gives me rise to this matrix M. So again, my matrix should be 2 by 4, and my columns, I index them 1, 2, 3, 4, and already I see what columns are linearly dependent and linearly independent. So for instance, you see that 1, 2 and 1, 4 are independent, but 1, 3 is not. It means that I can assume column 1 is 1, 0. It has to be, it cannot be the origin. It has to be something independent. And since 1, 3 does not appear in my collection of bases, what does it tell me about column 3? What shape does it have? So in other words, the fact that 1, 3 does not appear here tells me that 1 and 3 are linearly dependent. And so it has to be a multiple of column 1, exactly. So this should be something of the form A0, where this number A should not be 0. So it has to be a scalar multiple of the first one. And similarly, we see that column 2 and columns 2 and 3 and columns 2 and 4 are a basis. as well as 1 and 2. So certainly the fact that 1, 2 appears tells me that 2 and 1 cannot be parallel. So I can assume that column 2 has this shape. And also I can say something about how 4 looks like. How can I tell what shape does column 4 look like? It should be parallel to one of the previous ones according to this description. It should be parallel to which one? So it cannot be parallel with 1 because 1 and 4 is a basis. It cannot be parallel with 2 because 2, exactly, because 2 and 4 are a basis. So as Bernd says, it has to be parallel to 3. So this should be something like B0. And this is the shape of what, after row reduction, a point in the Grassmannian looks like in order to obtain this matrix. And then, if we would like this to be a positroid, all the minors indexed by these columns should be strictly bigger than 0. And that already is going to impose some conditions in A and B. So on one hand, since the determinant indexed by 2, 3 is a basis, so the determinant indexed by columns 2 and 3 has to be positive. That implies that A should be negative, right? On the other hand, or for the same reason, 2 and 4, so the determinant indexed by 2 and 4 is positive, then B should be negative. And 2, 3, oh, I wrote this. This should be a 3 for this to work, sorry. But then if we do this, the same analysis, then this guy is parallel to, now 2, 4 does not appear, so column 4 has to be parallel to 2. Sorry about that. And so this condition already we have written here, and now we also have that 3, 4, determinant index by columns 3 and 4 should be positive. And that determinant is A times B. So if A times B has to be positive, already we know A has to be negative. It means that B has to be negative. But also we know that 1 and 4, the determinant index by 1 and 4 has to be positive as well. And that implies that B should be positive. And that's not possible. Okay? So at least this example was small enough for us to convince ourselves that even though this matrix is linear, it is not a positroid. Okay? So it's a proper subset, and that already makes this definition worthy. Okay? Questions? Okay. So So one reason, so actually this definition I have given you of positroids. So positroids have like a very, very rich combinatorics, and part of their combinatorics is what I want to illustrate to you and show you how it can be used to prove properties about them and to prove that a given matrix is or is not a positroid. But actually, it also, in the second half of the lecture today, I will tell you how positroids arise from cell decompositions in the Grassmannian. And it's going to be like very superficial, but at least to give you an idea of why that's interesting from perspectives, not necessarily completely combinatorial, but also algebraic. So this definition is a definition, I should write here, Posnikov, about 205 or something like that. But there is also an equivalent definition by Bloom, although the way that he named them were not positroids but sortable matrix. So that was like another name that less known, but it's there as well. Okay, so let me just write down here the matrix that we just discovered is not a positroid. So I'll just write down the bases here. So 1, 2, 1, 4, 2, 4, 3, 2, 3, 3, 4. So this is the matrix we just discovered is not a positroid. So I'm just going to be abusing a little bit notation and say it like this. But now I want to draw your attention to this following example. And I want you to tell me what relationship you observe from this guy to the non-example that we just illustrated. So 1, 3, 1, 4, 2, 3, 2, 4. And I think this is the one I had written before. So this is a positroid. And one possible matrix that represents it, again, this already is very similar to what we did. And so I can represent it by this matrix here. The relevant maximal minors are strictly positive and the other ones are 0. And I want to ask you if you see any relationship between this positroid or this matrix and this matrix. So what kind of relationships you can see, if any? Anything that comes to your mind? I'm going to give you one, and then you can tell me if you see any other. So for one, so this matrix here, actually, I can think of this as a graph. So let me draw here. It has to be a graph with 4 edges and rank 2. And so this graph is a graphical representation of this matrix. You can see that 2, 1, 4, 2, 3, and 3, 4 are precisely the bases and the trees of the graph. Here, actually, this one happens also to be graphical. So 1, 3, and 1, 4, 2, 3, and 2, 4. So this graph happens to be a graphical representation of this matrix, although we know that not all matrices are graphical, but anyway. And so you see that what changed from one thing to the other was just a relabeling of the edges. And I think that's along the lines of what Kyle was saying, that there was a swapping of the columns. So these graphs, if we were to ignore the edges, are identical. As graphs, they are identical up to labeling of the edges. And that's something very important about positroids, that positroids really care about how you label your elements. With matrix, not so, because you certainly could relabel, if you have a matrix like the ones we have here, if you were to play with the columns around and switch places and stuff, you are going to have a matrix that is basically the one you started with originally, just stuff have been relabeled, but still a matrix. It's still a linear matrix. With positroids, that cannot be done. So basically, positroids are not closed under arbitrary reordering of the ground set. And already this illustrates an instance of that. So as matrix, these two matrices coincide, so they are basically the same up to labeling of the ground set. But if we are thinking of not just matroids but positroids, one of them is and the other one is not, because positroids really care about how you label your elements. And that also we can see from the very definition, because relabeling in terms of columns means you are swapping, you are doing some swapping. And if you start swapping columns, you are going to potentially mess up with signs of determinants. And so that can already destroy the property that you already had. Okay? Okay, so now I want to give you a couple of combinatorial gadgets that are very useful to me. They have been very useful to work with positroids, and you will see them more in context in the second part of the lecture. So right now I just want to give you the combinatorics without that much context, but I will do so in the next half of the lecture. So any question, comment? All good? Okay, so so before we do that, I would like you to recall how we defined an LPM. So if I have two subsets of a given set N, then I can define, if my subsets have the same cardinality, then I can define an LPM provided that one is smaller than or equal to the other with the relation we gave last time, just component wise. Then we just said that these two guys define a matrix. And so what is neat about this? Well, not only the graphical aspect that we explored yesterday, but also like from the matrix point of view, basically what this is telling you is that in order for you to understand this matrix, it was enough to know two bases. And these two bases allow you to recover the rest of them. And that's a very special condition. Like if you have if you have a graph, can you do something like that? Like, can you just have a certain set of bases and out of that set determine what are the other set of bases? That's certainly a very difficult question. And so this is one nice feature about lattice path matrix, that you already just with these little two pieces of information can recover the whole matrix. And or also with Schubert matrix, which we briefly mentioned as a subclass of lattice path matrix, where this L sequence was fixed to be the last k elements of your set, also satisfies this property. So with positroids, something like this happens. And again, as I said, this is going to make more sense in the context of the second part of the lecture. But basically, the first combinatorial object that we are going to introduce is an analogous of this. So it's a collection, it's a subset of the bases that allows you to recover the whole thing. Not only that, but it's also one way to determine whether or not a given matrix is a positroid. Okay? So this combinatorial object is what we call a Grassmann necklace. So let me first write the definition. That is going to look a little bit strange, but I think it's going to be more clear with the examples. So a Grassmann necklace a Grassmann necklace. Sometimes people say of type k comma n, where you will see what is this. So the n tells you that basically in terms of matrix we are going to be working with a matrix on ground set n, and the k tells you the rank. But just abstractly, this is in principle an n tuple, so there are here n stuff. Each one of these i's, I sub j, is a subset of size k of your set 1 up to n. So ij is a subset of n, and for such a tuple to be called a Grassmann necklace, it has to be the case that the following happens. So let me write you, and then you will see that actually it's easier than it appears. So if I happens to be in I sub I, then I'll write it like this so that it fits in my whiteboard. So I in I sub I implies that the next one, that I plus 1 equals it without I union some j and 2. So basically there are two situations. Either I is or is not in the ith subset here. So let me tell you what this means. So it's basically something that looks like this. So let's take 1 3 3 4 3 4 4 5 5 1. So what do I mean by this? I mean here I'm taking this tuple of 5 subsets. So here my n is 5, my k is 2. I1 is this guy, I2, I3, I4, I5. And I wrote here I5 as 5 1 and not 1 5 for reasons that I'll tell you later, but basically this is just the subset 1 5. And basically this condition is telling you that how does each of these subsets behave with respect to the previous ones. So for instance, when you are looking at how you pass from I1 to I2, so this guy is I1, this guy is I2. So basically, the fact that 1 belongs to the first piece means that in the second piece, you are going to drop out that 1. So now 1 does not appear here, and you are exchanging it with some j. So this is what the first condition tells you, that 1 is now disappearing from the second piece and being exchanged by someone else. The pass from I2 to I3 now tells you what? Since 2 is not here, then the next subset equals I2. So that's why these two guys are equal. Now the pass from I3 to I4, so 3 belongs to the third piece, and it means that in the next one, you are just going to drop 3 and change it by someone else. And in this case, we're changing it by 5. And so on. From I4 to I5, same thing. 4 is here. It means that it's going to be changed to construct the next one. And in this case, we change it by 1. And we do this cyclically. So we are taking indices modulo n, basically. And so we compare now I5 with I1. So 5 is here. It means that in the first piece we're dropping 5 and we're exchanging by 3. It looks weird, but let me tell you how does this make sense with the examples we have just built. So where did this come from? So these actually are going to come from positroids as follows. So if we were to look at what we did in example 1, also we have it right here. Yes. So in example 1, we had it right here. We had this matrix here. And basically, whenever we have a representable matrix, whether or not it's a positroid, we're going to be able to build a Grassmann necklace. How do we build it? So what we're going to do is we're going to codify what are the, if we were to read from left to right, we start looking at where are the first basis vectors, in which column they appear, in which columns they appear. So if we were to start with this matrix, I'm going to start building the Grassmann necklace, and we are going to obtain the one that we just provided there. So for the first piece, I look at my columns, and then I wonder where do I have, if I were to look at this, then I wonder where are the first two, from left to right, the first two columns that are linearly independent, or the first two basis vectors. And from left to right, the first two basis vectors are in columns 1 and 3, right? 1 and 2 is not, and 1 and 3 is. So that's the first basis vectors where they appear. Actually, I'm going to write this right down here. So that gives me my I1. Now I want to build I2. So what we are going to do is so that's what I usually do. For I2, we start reading, in the first step, we started reading 1, 2, 3, 4, 5. For the second step, we are going to start reading 2, 3, 4, 5. And I'm going to put here a copy of the first column. It's like if I were to do, I'm going to do cyclic shifts at every step. So now, and I'm going to change here the sign. Don't worry too much about the sign just yet. But anyway, so now my matrix is this one. I just did a cyclic shift of the first column. And I ask the same question. Where are the columns that give me the first pair of basis vectors? 2 does not give me with anything, so I have to start with 3. And it so happens that 3 and 4 are the first two basis vectors that show up. Now I'll do the same to build the third one. So I'm going to put a copy of the second column. I just cyclically shift it to the end. And now I'm looking at my matrix, but now the columns are 3, 4, 5, 1, 2. And I do the same. Where are the first basis vectors that appear when I read starting from here up? And I see that they are in 3 and 4. I do the same with 4, so I'm going to put now here a copy of column 3. I'll tell you about the sign in a second. And I do the same from 4, 5, 1, 2, 3. Where do my first vectors of bases of the column space appear? And I see that 4 and 5 are the first ones. And last but not least, then I put here a copy of the fourth one. And in my matrix here, so now that's my final matrix indexed by columns 5, 1, 2, 3, 4. And then I ask the same question, and I see that my columns, my first two columns that form a basis are column 5 and 1. And so here, that's why it recorded it before like 5 and 1. And you see that this actually matches the example that we did here of the Grassmann necklace. So, as I said, this is something you can do with any realizable matrix, because all I did was just start with a given matrix that realizes it, and keep cyclically shifting columns and just recording where, basically, if we were to start with a given reading from a point up, the question that we were just answering was, if we were to do row reduction, where are my pivots? So in the first row reduction, pivots were in columns 1 and 3. In the second row reduction, pivots were in 3 and 4, and so on. So basically, if we were to give 5 different orderings of the canonical basis, so this would correspond to the usual ordering, E1, E2, E3, E4, E5. This would correspond to ordering the canonical basis, first putting E2, E3, E4, E5, E1, and so on. So basically, you have 5 different orderings of the canonical basis, and for each one of them, you ask yourself, where are my pivots when I look at my matrix? That's the question you are answering. And that gives you a sequence of subsets of the same size, and that sequence of subsets satisfies the definition of what a Grassmann necklace is. Now, the key point here is that, as I said, this works for any representable matrix. You can play the game with any matrix of your choice, but already we know that not all representable matrices are positroids. So how does Grassmann necklaces distinguish representable matrices that are not positroids? So that's what I want to tell you now. But before doing that, is there any question? Is it clear how we build the Grassmann necklace in the example we just gave? Yes or no answers, or more or less, are welcome. Okay, thank you. More or less, okay. So let's just, for instance, check that we know that I2 is what we claim. So if we want to build I2, this was my original matrix. And to build I2, then my original matrix has columns 1 up to 5. To build I2, what we did was bring this all the way to the end. That gives me this matrix. Now the columns are ordered differently. And if I were to look at my matrix like this, then I'm going to do row reduction. If I were to do row reduction, I just want to locate which columns contain the pivots. And if we were to do row reduction, columns that contains the pivots are going to be columns 3 and 4. And that's what we recorded here. So this just records positions of pivots with a certain ordering of the canonical basis. And I did not explain the sign here, but basically, since so the sign only matters when you are actually computing the Grassmann necklace of a positroid, because if you were to do this cyclic shift, you need to keep guaranteeing you need to keep guaranteeing positivity of certain determinants, and you can do this cyclic shift up to a sign. So the sign depends on the rank. That's not too important right now. But what is important at the moment is that we know how to obtain Grassmann necklaces. So is it better now? Okay. I don't see otherwise, so I'll continue. Okay. So, in the example we just did, so let's go back to it for a second. So this was the Grassmann necklace we obtained, and certainly you can see there are some repetitions. And if you compare the collection of the elements that appear in the Grassmann necklace with the collection of elements that form the basis, you see there is an overlap. And actually, any stuff in here, any element in the Grassmann necklace is a basis, and that precisely comes from the way we constructed it. But also notice that there are some basis elements that did not appear here. So for instance, 1, 4, 1, 4, 3, 5, 1, 4, I think those were the two that did not appear, okay? So this is a subset of the bases that when you are a positroid is enough to recover the whole positroid. In this case, given this, we are only missing 2 pieces of the information, but in the case of positroids, this is going to be enough. Just as with lattice path matrix, given U and L was enough to recover the whole matrix, in the case of positroids, given the Grassmann necklace is enough to recover the whole positroid. So I want to show you how this is done. And okay, so it's 250. So let me just write down what's the condition, and then we will take a little break. So okay, so let I1 up to IN be a Grassmann necklace. Then, or let me say, let B be the collection of, so if my Grassmann necklace is of type Kn, so if each of its elements has size K, so let me take the subsets of N that has size K, and I want to determine which ones are going to be the ones that correspond to the positroid that the Grassmann necklace gives rise to. And this is, again, something similar that happened to the case to lattice path matrix. So basically what I want to do is, for such a subset to be another basis, it has to be bigger than or equal to each element on the Grassmann necklace. The only thing to keep in mind is that when we build each of the elements of the Grassmann necklace, we build this guy according to the usual order, 1, 2, up to 5. This one according to the order 2, 3, 5, 1, etc. So that's the only thing that's going to change. So then we are going to say that then sorry, I said nothing here. So let this be, let me write it like this. So subset of N of size K such that, so the condition now is that B is bigger than or equal to I sub j for all j. And this bigger than or equal, I'm going to put here a sub j where this order sub j is with respect to j is the smallest one, then is j plus 1, then n, then 1, then j minus 1. So basically what I'm saying is that see, if I take b equal to 1, 4, then I want to compare b to, with respect to this Grassmann necklace, to the usual order. So I want to compare 1, 4 with the order 1, and it has to be bigger than or equal to the set 1, 3. So component wise, this is the case. And here the underlying order was this. For the next order, now my underlying order is this, 5, 1. And I have 3, 4, which is the second element. This was the first one. This is the second element in the Grassmann necklace. And I want to compare it with B, which according to this order, I'm going to write as 4, 1. And we see that component-wise, 4 is bigger than or equal to 3 in this order, 1 is bigger than or equal to 4 in this order. Let's do one more. I3 is 3, 4, and I wanted to compare it according to the order 3 to B, and the order 3 is this. Five, 1, 2. And again, similarly, component-wise, it holds. And the same holds if I were to do I4 and I5. So what this is telling me is that if I have a Grassmann necklace, then this collection of bases, this collection of k-subset that satisfies that the subset is bigger than or equal to each one of the ij's with the corresponding order, is the collection of bases of a matroid. Then this gives rise to a matroid. A matroid on ground set N with this set as bases. And basically this is one way of characterizing positroids. If you are given a Grassmann necklace, then a representable matroid is a positroid if and only if this collection matches your collection of bases. Otherwise, it's not a positroid. So we're gonna continue on this after the break and see with our non-example why in the non-example this condition fails. Okay, so maybe it's a good point to take a pause here, and actually, so the exercises will postpone them a little bit toward the end. And so how about 10 minutes? So I think, so 10 minutes from now is, I'm confused with it. Okay, yeah. So at 3:05, is that okay? Yeah. Okay, so 3:05 we'll be back. And please bring questions, okay? Okay, so this last part, as everything with practice it becomes better, also because we are not used to thinking of things ordering in this way. So if you practice a little bit this ordering, it's going to be easier as everything, no? Okay, so again, so the takeout from this is that so a linear matroid is a positroid if its collection of bases, B of M or B, coincides with those obtained as in this description. So basically, again, what we are saying here is if you have a linear matrix, then you have a matrix representation of it. Given your matrix, you can obtain its Grassmann necklace. Given your Grassmann necklace, you can then ask what bases are bigger than or equal to each one of the components with the corresponding order, and all that collection is the collection of bases of a matrix. This tells you that if your original matrix has as basis set matching what you produced, then your matrix is a positroid. Otherwise, it's not. And in the non-example, so I erased it, but let's put it here. The non-example, we had the matrix was given by this matrix or something like this. So we had 1, 0, 0, 1, A 0, 0, B, and A and B are non-zero. So if we were to obtain the Grassmann necklace out of it, we are going to get 1, 2, then we are going to get 2, 3, then we are going to get 3, 4, and then we are going to get 4, 1. And again, I have done this many times, so I know how this goes. But anyway, this is going to be the Grassmann necklace. And on the other hand, if you were to take the uniform matrix U24, which is also representable, its Grassmann necklace is this one as well. So these two Grassmann necklaces are the same, even though these two matrices are very different. This one has all the possible subsets of size 2 as bases, this one does not. And so what happens is that when you take what bases this Grassmann necklace produces, it produces all the possible subsets of size 2. So let's call it I sub m. I sub m gives rise to all the subsets of size 2 out of the set of size 4. And we know this is not the collection of bases of my original matrix, so that's what happens. The fact that this is not a positroid tells me that what I obtain from the Grassmann necklace is bigger than the collection of bases of the matrix itself. So that's another way of testing whether or not a given linear matrix is a positroid without having to come up with a matrix representation. And maybe this characterization or this combinatorial tool may not look too combinatorial for you. It doesn't look like that for some people. For me it does, but anyway. But another one that may be more combinatorial for most of you is one that comes from permutations. So let me, using this example, give you what I'm going to call a permutation, a decorated permutation. So basically, a decorated permutation is a permutation. In this case, is going to be a permutation on the set 1 up to 5, because my ground set is 5. And the decorated part means that fixed points, every time I have a fixed point, is going to have one of two possible decorations. And so I will decorate either with an overline or an underline. So let's see in this case how we are going to obtain, given the Grassmann necklace, the permutation. So basically, what we have observed before is how we passed from one subset of the Grassmann necklace using the previous one. And that's what will give me my permutation. So in this case, let me, by example, build it for you. And so, in the first step, what did we do? We deleted 1 and we introduced 4. Or in other words, we took 4 and replaced it by 1. And it means that in my permutation, the image of 4 is going to be 1. Okay? So that deals with the first one. It just illustrates what exchanged we did. So we introduced 4 and we deleted 1, and that's what we did here. In the second step, the fact that 2 does not appear in my permutation, in my subset, means that 2 is going to be a fixed point, and as I said, my fixed points will have 2 decorations. In this case, I will put an underline decoration. And why will I put an underline? Because the fact that 2 is not in I2 tells me that I will decorate it with an underline. If 2, the opposite, the extreme opposite of that situation is that an element appears in every one of the elements of the Grassmann necklace. And in that case, that element will be a fixed point, but overline. In this case, it's going to be an underline because it does not show up, even in the one that it should appear, potentially. So now let's look at what we did when we pass from I3 to I4. So from I3 to I4, I exchanged the 5 by the 3. So it means that the image of 5 is going to be 3. And passing from I4 to I5, we did what? We exchanged 1 by 4. It means that the image of 1 is going to be 4. And cyclically, what we do when we arrive to I1 from I5 is that we switch 3 by 5. So 3 took the place of 5. So the image of 3 is 5. And this is my permutation, okay? Is, at least in this example, clear for you how we obtain it? Okay. And just Bernd or the others too? Okay. So, so maybe if we go here, so you can see this picture on this side. So what do we have here? You can ignore all these connections. You can ignore the positive structure for a moment. But basically what you have is all possible decorated permutations on 3 elements. So you see the usual permutations, in this case permutations on 3 elements, are just 6 of them. But now that we are choosing to decorate fixed points by underline or overline is why we obtain here so many. So here the notation I'm using for permutations is the one that I have here. So is what is known as the one-line notation. So if I had given just this, what this means is that 1 goes to 4, 2 goes to 2 underline, 3 goes to 5, 4 to 1, 5 to 3. And this is what I have here. So I have here every possible permutation on 3 elements, decorated permutation. And basically, each one of them codifies all the possible positroids on 3 elements. So here you have all the positroids on 3 elements that there are. So basically, on one hand, positroids can be encoded either by Grassmannian necklaces. So there is a bijective correspondence between positroids on ground set N and Grassmannian necklaces on N elements. And there is also a bijective correspondence between decorated permutations on 5 elements and Grassmann positroids on 5 elements as well. So here you have all the possible positroids on ground set 3. And tomorrow is going to make sense what these connections are. But as of now, what is important is that here we have them all. And so one thing that you can draw out of this is that given that each one of these guys codifies a positroid, you might want to know what that positroid is. Namely, you might want to know what the bases are. And I may tell you later how to obtain the bases. At least I have shown to you one way of going from the Grassmann necklace and the permutation. But as I said, this correspondence was bijective. But anyway, keep this picture in mind, and maybe you can start ask yourself many questions about this. In particular, so for those of you that are enumeratively inclined, in this case, if you were to look at the way I have drawn this picture is like by floors or ranks, as we would say in POSIT terminology. So here we have 1 element in rank 0, 7 elements in rank 1, 7 elements in rank 2, 1 element in rank 3. So if we were to count things by rank, we see that the sequence of elements by rank is actually palindromic, and that's something that happens in general. So anyway, this is another one of the combinatorial objects that is certainly more compact. It is more compact having a permutation than a bunch of subsets codifying a positroid. So in terms of simplicity, this has all the information you need to recover your positroid, and it's more manageable than this. But I have also come to realize that knowing not just one way of understanding positroids, but more than one, is very useful, and that happens usually with matrices. So it's good to be a little bit, to move around and find what's the right gadget for you. So these are just two of the many combinatorial objects that encode positroids. There is also polytopal characterization of what positroids are, but I'm not going to go into details. I can tell you references if you're interested, but at the moment, so is it clear how we build the permutation? Yeah, so yes, so let me clarify the fixed point thing. So, so here, let's look at our original example. I'm gonna erase these guys here. Okay, and I had here 1, 0. So this was our original example, and the permutation that we just associated to this positroid is the permutation 4, 2, 5, 1, 3. So the fixed points, so if we have overline or underline, this is due to what? So the underline, which was the case here, if you have a matrix representing your positroid, the underline means that that column is the 0 vector. In matrix language, what we would say is that that element 2, is a loop. If you were to have a graph, what you would see is that that edge is actually a loop. And what that means from the, say, basis structure of the matrix is that this guy being the 0 vector does not show up in any basis. It does not appear anywhere. So these are fixed points are either stuff that do not show up in any basis, and we are going to say that this is a loop. So that means I is not in B for any B in the basis set. And the extreme case is that I appears in every basis, and that's what we call a co-loop. So I shows up in B for all B bases. So in graph terminology, loops are co-loops are edges that are required for any tree of your graph. So those are how the fixed points come up. And in the Grassmann necklace, we see already that the situation that we had for our positroid was that, so the Grassmann necklace is not here anymore, but we had that the fact that 2 did not show up in the second position already is going to tell you that 2 is going to be a loop, because there is no way that when you start reading your matrix from here up, you are going to obtain a pivot here. And if you are not able to obtain a pivot in that first column, means that first column has to be the origin. Okay? So that's the idea of the fixed points. And so going back here, maybe we can do a little test. So I don't know if you are able to see here, but this is the permutation, the identity permutation. So every point is fixed, but here we have decided to color those 3 fixed points with underline. So if we are decorating those 3 fixed points with underline, it means that my matrix is a matrix on 3 elements. But how do those 3 elements look like? So, any idea? While I erase the blackboard. So the fact that the 3 points are loops because they have underlines means that the 3 of them, if we think in terms of vectors, the 3 of them are the origin. So that's what would happen. And the extreme is that the 3 fixed points, if we were to have this one that was the other extreme case, it means that all my points belong to, you can think of this as, this is a matrix on ground set 3 of rank 3, and this is going to be, for instance, just the identity. So my 3 elements belong to the only basis, and if you were to think in terms of graph, this also happens to be graphical, and is going to be a single path. And here was the other extreme we were just mentioning a second above. So this is going to correspond to the 0 matrix. Usually we don't even bother on writing it because, so you can think of it in terms of graphs as just 3 loops, 3 little loops. And so here you can start seeing that for each one of them you can tell whether your element, if it is a fixed point, whether your element is a loop or a co-loop, okay? And so I will tell you more about this picture tomorrow. One thing to point out, that I want to point out, is that the way this is drawn is precisely illustrating one important thing that will be more relevant from what we will do in the last 2 lectures. But basically, already this again illustrates all the positroids on 3 elements. And on 3 elements, what are the possible ranks of a positroid? Either full rank, so either rank 3, or the positroid has rank 2, or the positroid has rank 1, or the positroid has rank 0. So basically this picture drawn like this is telling me, oh, here I have the positroids, namely the points in the non-negative Grassmannian 1, 3. These are the points in the coming from the totally non-negative Grassmannian 2, 3, and this point in the totally non-negative Grassmannian 3, 3. So, and the drawing we have here is going to correspond to flags that we will define in the last. Tomorrow at least we'll talk about them. But basically it's going to be sequences of vector spaces chaining to one another. Okay, so the families that we have already seen before, one of them given by LPMs actually are positroids, and you can prove this directly from the definition. So there are ways of coming up with matrices that give you a representation of any LPM, matrices that are of the type van der Monde. I won't do it here, but this is something that is known. Or you can also do it through the Grassmann necklace description, although that's a bit more tricky. But again, providing whether or not a given family of realizable matrices is or not a positroid from the matrix point of view is already tricky. But this is a fact, and of course, I will say, since Schubert matrices live inside LPMs, they are as well. So since uniform matrices are LPMs, so one thing that one might wonder is how the different objects that we have associated to it look like. So on one hand the Grassmann necklace, and on the other hand the decorated permutation. So in the case of uniform matrix, one thing that you can look into is, so here I'll go up to K, is convince yourself that the permutation associated to it is a permutation with no fixed points, and it doesn't have fixed point on one hand because there are no loops in the uniform matrix. Every element is in at least one basis, so there are no loops. And there are no coloops because there is no element that appears in any given basis. So it has no fixed points, and actually it looks like this. So I need to, so basically what we do is that here are going to appear numbers 1 up to whatever this is. This should be something like n minus k, maybe. I don't know. Anyway, so here is the first of this sequence of numbers, and then you continue here, n minus k plus 1 up to n. So you can correct me on this last element. And so in the drawing I had shown you a second ago, so you will spot right away where the uniform matrix appear. So anyway, one thing that I wanted to achieve with positroids, so the reason I became interested on them, on one hand was because of the combinatorics. Their combinatorics, as I said, there are lots of families that we can play with associated to positroids, and that was very appealing to me. And on the other hand, I want to at least give you an idea of how all this came up in the context of the composition of the Grassmannian. But before that, I should mention that if you were to read the literature, sometimes there is no like a unique way of associating a decorated permutation to a given Grassmann necklace. Sometimes, if you were to look in some other papers, this won't be the permutation associated, but it's inverse. I prefer to do this one because for me it's easier to recover the Grassmann necklace out of this one than its inverse. If I have time, I will show you how to go backwards, but at the moment, just a word of warning in case that you look up other references. So, okay, so basically there is a nice dictionary that I became interested on between geometry and matrix. So already we have seen that every point, and remember we are doing everything over the reals in particular because for positroids we needed the non-negativity condition. So we already know that each point in the Grassmannian gives rise to a matrix representable, or I'll say linear, and every linear matrix arises this way, or any representable matrix over the reals arises this way. So this is like one way to pass from one side to the other. On the other hand, if I pick a point in the non-negative part of the Grassmannian, then we obtain positroids, and every positroid arises this way. And this description of what a Grassmann necklace is and what was the definition of lattice path matrix and everything certainly is fun from the combinatorial point of view, but sometimes it's also nice to know a little bit more of the context on how people started thinking about those stuff. So here, one thing that I learned on the process was that on one hand, so let me call it MULK. So let me take a Schubert matroid, and let me take an arbitrary LPM. So basically, if I have here an LPM, given that we know that they are representable, and so they are, so we would like to know what the dictionary tells me, what corresponds on the left-hand side. And so here, to fill this spot, I'll just tell you a little bit about how the dictionary goes. So this part is going to be, we're going to think of it in terms of the Grassmannian, the usual Grassmannian. So let's consider GR24. So two-dimensional subspaces inside 4 space. So let's take V here, okay? And now we want to wonder ourselves what are the possibilities of how V looks like when we obtain a reduced matrix representation of V. So the possibilities are the following. So 1, 2, 3, 4. So one thing that may happen is that if I take a matrix that represents V and I row reduce, pivots are in the 2 columns. If pivots are in the 2 columns, my reduction looks like this and stuff here. Okay, that's one option. So in this case, what is important is that pivots were in columns 1 and 2. Another possibility is that pivots were in columns 1 and 3. So if pivots were in columns 1 and 3, the identity matrix will show up in those columns, and the reduction is going to look something like this. And so that's another possibility, and so on. So for the case where my pivots appear in columns 1 and 4, this would be the picture, and then I'm left with 2, 3. If it were the case that my vector space, after reducing any matrix representation, has pivots in columns 2 and 3, it means that column 1 is the origin, and then in 2 and 3 I have the identity and stuff here. Similarly with 2, 4, so the origin here, the identity in columns 2 and 4, something here, and finally 3 and 4. So in 3 and 4 I have the identity and nothing here. So whatever point I grab in the Grassmannian 2-4, that point is going to fall in one of these situations. Not in 2 of them, just one of them. And certainly here we are again thinking that our canonical basis is order E1, E2, E3, and 4. But with that ordering, my point in the Grassmannian will fall only in one of these places. So that means that I can partition the Grassmannian into pieces, and those pieces is going to be indexed by either one of these subsets. So if I were to think of the Grassmannian 2-4 as a cake, that cake, at least one way of dividing it or splitting it is I can split it in 6 pieces, and each piece is going to be indexed by a subset, let's call it U, and either my subset is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So that's one subdivision, one partition of the Grassmannian, and whatever the point I started with looks like, I am able to put it in only one of these pieces. So you see that when we describe the general row reduction in each situations, some stars appear, and those stars are potentially whatever. They are real numbers, whatever they are. But what happens is that then one way of defining Schubert matrix in this context is that what is a Schubert matrix? A Schubert matrix, from our point of view so far, is a matrix that has an upper path, and the lower path is always fixed. In the case that we are at hand, we are in the Grassmannian 2-4. The lower path will always be 3-4, and the upper path is the U1 and is the one that may change. So U can be either 1-2 or 1-3 or 1-4 or 2-3 or 2-4 and 3-4. So for instance, it could be this, and if it's this, so this is 1 and 3. And so this is a Schubert matrix for us, but in this context, or in this dictionary, Schubert matrices can be thought of as points that are that correspond to the piece in the Grassmannian indexed by the subset U that defines my matrix. So people sometimes say Schubert matrices are generic points inside the cell, the Schubert cell indexed by 1, 2. And that's the way of saying that if I were to think of, for instance, stuff that look like this after row reducing, it means that from the matrix point of view, I'm thinking of the Schubert matrix indexed by the upper path 1, 3. So I will be thinking of this Schubert matrix. And already you see that this picture here, if I were to ignore where my pivot was, looks like this picture here, only upside down. And again, if you were to think of the Schubert matrix, let's say the Schubert matrix two, 3, so 1 is not the piece here. This 2, 3 corresponds to this diagram, and you already see it here. So anyway, the combinatorial way for us of thinking of Schubert matrix is nothing but how a generic row reduction in the Grassmannian looks like when we are thinking of the column set here indexing our upper path. So basically, Schubert matrices arise as generic, and I will just throw that word here, generic points in the Schubert decomposition, in Schubert cells. And similarly, I'm just going to say here that lattice path matrix can also be defined as generic points in a different decomposition that is called the Richardson decomposition. So one thing that I would like to point out is that when we partition the Grassmannian like this, we partition it into pieces. What was each piece indexed by? Each piece was indexed by a subset of size 2. And what was that subset of size 2 telling us? It was telling me, oh, I'm looking at points such that when I row reduce, pivots are in columns 1 and 3. But I again row reduce with respect to a very specific order of the canonical basis. And then people start saying, okay, why are we privileging the canonical ordering, the usual ordering of the canonical basis and not other orderings? So if instead of ordering the canonical basis the usual way, E1, E2, up to En, why don't we order it En, En minus 1, like going backwards? And if we were to do that, that would mean, more or less, that not only you are thinking of row reducing from left to right, that would be the canonical order, but you are also thinking of looking at pivots from right to left. That would be the reverse ordering. And so you could play the same game, And basically, when you play that game, similar to what we just did, that's another way of defining lattice path matrix. So lattice path matrix are matrices that come from the Grassmannian in such a way that U tells you where the pivots are when you look from left to right. L tells you where the pivots are if you were to do the reverse ordering. And that's also another nice decomposition on the Grassmannian. It has many properties, etc. And so, you know, we mathematicians never stop. And so, okay, looking at those two orderings is not enough. Why not looking at different more orderings? That's where positroids came in. So this Grassmann necklace is nothing but, as we did before, telling us a sequence of objects that tells you where pivots appear, not with only with the usual ordering of the canonical basis, but with m possible ordering of the canonical basis. What m possible orderings? The ones we had before. The canonical one, then the one that is cyclically shifting 1 to the n, then cyclically shift 2 to the n, and so on. So that's another way of defining positroids. Positroids are I could have put it here, positroids are the generic points in non-empty cells in the Grassmannians after doing the positroid decomposition, and the positroid decomposition is that intersection of Schubert cells. I'm throwing a lot of stuff in here, but my point is that there is really a very, very nice dictionary between geometry and matrix, and it was this dictionary that made me particularly interested in positroids, because already they have lots of combinatorics that regular matrices, that usual matrices do not necessarily have. And so if they have so much combinatorics going around, maybe you could understand things better for positroids that you may not understand for other kind of matrices. And so that was like the starting point for me for the results I want to show you and share with you in the last 2 days. So keep this picture in mind, because what we're gonna do tomorrow in particular is, already we have built like, or say highlight, this is not my work, this is work of many people in the past. But basically we have a dictionary between Grassmannian matrix, representable matrix. We want to extend this dictionary, and we will move from the Grassmannian to something called the flag variety. And so that's what we are going to do tomorrow, and I want to show you this over here. So I'm afraid the first question you won't be able to do just yet with what I told you to. If you're interested, I can tell you how to go back and forth from decorated permutations and Grassmann necklaces, but that's not going to be, at least for the rest of what we have today, just a couple of more minutes. But I want to draw your attention to part 2. So here in part 2, you have 3 matrices. They are 3 matrices on 4 elements and different collections of bases. And you're asked to determine whether or not they are positroids. Already you have tools to do that. But the nice thing about this is that I don't know if I should spoil the answer, but you will see what happens with them, and ask yourself, or one thing that is very common to ask oneself when you are working with matrices and things like that is, say you have a specific family of matrices you care about, in this case positroids. Already we have ways of determining whether or not a given matrix is or not a positroid. But for instance, if you're familiar with graphs, then you know that there is this very famous theorem on graph theory that tells you how you can determine whether or not a given graph is planar. So when are you capable or not of drawing a graph on the plane without crossing of the edges? And that can be done just by saying that your graph has to avoid these two minors. So basically what I want you to think of is in the question of whether you're given if you're given a matrix, whether or not you can determine it is a positroid just by looking at whether or not your matrix avoid certain patterns inside. So if you're not familiar with, if you have just become familiar with matrix this week, this might be a little bit too up in the clouds, but if you're familiar with matrix minors, then that only says that there is a characterization of positroids by looking at minors that a matrix should avoid in order for it to be a positroid. So that's more or less the spirit of question 2. Question 2 is already easy for you to answer, but it goes beyond just determining whether or not they are positroids. It goes toward a characterization of positroid via minors. Okay, so is the Richardson decomposition cellular? I don't know. No, I do not do algebraic geometry, and the little I know, I have already shared with you. So I don't know. I don't know. So is there any other question? Okay, so it would be nice if you have the chance to work on some of the exercises to let me know. I know that this might be too new for many of you, but at least if I'm able to convince you that not just matrix but positroids are very interesting, I'm happy. So is there any further comment or question that anyone has? Okay, so is it clear for you how to determine whether or not the matrix from the exercises can be, how can you determine whether or not they are positroids? If not, try and let me know what's the difficulty. And we can talk about that tomorrow. Okay? Okay, so that's it for today. Thank you very much.